Hi everybody, welcome back to the bench. I've been working on a little project here, and it's actually an evolution of a project that I've been working on for quite a while. And I've just had some extra time now because I'm very busy with work, so I have not started any big projects on the bench, as you've noticed lately. So it's given me some extra time to do some of the little things that I've been wanting to do. You've seen the last couple videos I've done have been maintenance videos, for instance on my test equipment and on my bench amplifier, or I should say my desk amplifier that I connect to my computer upstairs. And in the last few videos, I've really developed the need for a buffer preamplifier, is what I'm going to call it. So if you go back to the Scott 399 video series that I did, one of the things I wanted to do was record the stereo output from the record out jacks on that 399 and pipe them directly into the camera. Now, part of the problem with that is the input impedance of the camera and the sensitivity of the camera is not very well matched to the output impedance and the output level of the record jacks on the Scott 399. The other thing that we run into is when we do recordings, sometimes the offset of that recording is off. And one of you viewers mentioned in one of my videos, touched on this subject a little bit, and I said this is a really interesting thing that'll fit in to this project that I'm working on. And what I mean by offset is I've noticed in some instances when I make a recording to embed in the video, a lot of times when I'm looking at the little spectrum on the recording track when I'm using CyberLink, I notice that I'll have asymmetrical clipping. In other words, if I turn the level up of the audio too high, there'll be plenty of space on the top, but on the bottom part, or vice versa, I'll be getting clipping, instead of it clipping equally on the top and bottom of the waveform. And this is due to what's called offset. So offset can sometimes take place as a result of the microphone that you're using. For instance, if you have one of those little electric microphones like this one that uses a battery, sometimes the output of it can be a little bit, have some DC offset to it. It doesn't hurt the input device or anything, but what it does do is it allows for asymmetrical clipping, especially when you have something with a high record level. So what ends up happening is, to prevent that, you shrink the record level down even further than it could be, which really doesn't hurt anything. But it would be nice to be able to get rid of that. So a couple things that we want to do is, it would be nice to have a device, a little preamp, a little line stage, we call it a buffer preamp. It really doesn't amplify the sound as much as it will either attenuate it, or it will isolate the impedance of the source from the impedance of the input. And that's really the goal of this. Now, this originally started as a project for the Fisher 500, which was a mono receiver, when we have all stereo sources. So what I wanted to do is I wanted to very accurately take a stereo source and merge it into a mono source. Now, the easiest way to do that is just to use a couple of resistors. So you take your right and left channel audio, run them through, let's say, a 1K resistor each, tie them together, and there you go. But that has its own issues, attenuation being part of it. But we want a little more accurate way of doing that. So I came up with this little thing. I'll show you this in a minute. This was the first device. But then I still wanted to have a stereo device that could buffer a stereo signal between the source and the input, and also to be able to just remove that offset, so that if we have something, you know, coming out of, let's say, that receiver that I'm feeding into the microphone input of my camera, I can do that. I can adjust the level, and I can isolate the impedance mismatch. That's what this video is about, and it has evolved. You know me, I start on a project and then it kind of goes in its own little tangent, which is what happened here. And it ended up, I have a really nice little piece of equipment for the bench now that maybe you'll be interested in seeing. So that's what this is about. And if that sounds interesting to you, stay tuned. This is what we're going to look at. Now, the first little device that kind of inspired the idea for this whole project is this one. And this is something that, very simply, it's just a little op-amp circuit. And I think I'm just using something, I don't know if it's like a 741. I don't think it's a 741. It's actually a NE, like a 5532 op-amp, because I have a bunch of those. And all it's doing is you just take it's taking the two stereo signals, kind of putting them together, and then outputting them as a single mono signal. It uses a split power supply. So you have a positive and negative 9 volts, and that's just done by two 9-volt batteries. Of course, nothing is quieter than a battery. And I just put a little on-off switch, and there's an attenuation knob to set the attenuation of the signal. And this was really nice because I could take any signal that I had, whether it was my MP3 player, my mobile phone, the computer, sound card output, anything, any line level signal, I could feed it in here in stereo, and it would come out as a very good sounding mono signal that I could feed into, like the Fisher 500, for instance. The main reason this was originally built before the 500 Fisher was little projects like, I don't know, something like this, where you have a little AM transmitter with modulation, and it's, you know, it's mono. So I wanted to be able to have a nice mono signal that I could derive from my stereo sources to drive that little modulation. So this worked out really well for that. Now, this is kind of tightly packed in here. It was made on a little perf board, little proto board, and all the wires are kind of tightly crammed in there. I don't really like to take it apart because of how tight everything is. But I'll show you the next thing that I built, and it just goes from stereo to stereo. So instead of merging those two signals together, they're just passing through as right and left channel. So let's take a look at that. Here's a little schematic that I sketched up on KiCad. And if any of you have ever worked with KiCad, you'll know what I'm talking about. It's a nice freeware program that you can download, and it'll let you draw schematics, and it'll let you draw the circuit boards or lay out the circuit boards, and even turn them into Gerber files if you want to have them sent off to be printed up. But here is the signal, or the circuit, and all it is two dual channel op amps. And in this case, I'm using the NE5532 because they're very inexpensive, and for what they are, they work very well for audio. Now, of course, if you want to buy a $50 op amp chip, knock yourself out. But for what we're doing, this is more than adequate. And it's a very simple circuit when you see this. The way we did this is you have your input is going across a 10K potentiometer. So this is a 10K input impedance. It really doesn't matter. I mean, I know some signals are higher impedance and some are designed for lower impedance, but this 10K pot going directly to ground like this it'll ensure that the signal is relatively low noise. We're going into the inverting input of this op amp, and some of you might say, well, why not go into the non-inverting? Because now, since this is inverted coming out of here, if we want it to come out the same way, we have to put it through a second stage and invert it once again in order to get the output to be in phase with the input. Well, if you read up on these op amps, and I'm not going to get into real great detail on this, but the input impedance and the way that it works between inverting and non-inverting input is different. So for instance, if we go into the non-inverting input, the input impedance will be different, and it will allow for at least a slightly higher noise level. So this is actually a superior way to do this. Also, we're doing this in 2 stages. If you want to add a little bit of gain to the circuit, we can add it to this second part here, and we're not playing around with it here with regards to the input. Now, I don't want high gain on this because this is really not about gain. This is more about buffering the input from the output. So no matter what kind of load I put on here and what kind of load this puts on the source, they're going to be kept independent of one another. And this circuit is not going to care about it. That's the beauty of all this. It's also going to be very low noise. Now this 4.7 microfarad capacitor that's at the front end, it keeps a very flat transfer of signal from here to here all the way down to about 10 hertz. And it also will transfer a very flat signal all the way up to well over 100 kilohertz. So we get the entire audio spectrum with a very flat response curve. And that's important because you don't want this to color the sound in any way, or at least any more than it absolutely has to. All of the resistors in here, if you notice, are 10K. And if we do this in this manner, technically this should have unity gain. In other words, none of this should not cause any gain in the circuit. It should just pass through 1 to 1. So if I put 1 volt peak to peak of signal here, I should get 1 volt peak to peak signal out. Now if you notice on the second stage though, I added a second 10K potentiometer in series with this. What this is going to allow you to do is you can add a little bit of gain, and this will, in theory, this should add about 3 dB of gain. In reality, it's not quite that much. There are some losses, a little bit. The other thing is, when this is turned all the way down, this is not true unity. In other words, you will get a little bit less signal out than what you're putting in because there are some inherent losses. So this little gain stage allows you to compensate for that a little bit. So I decided to mock this up and make something for the bench, and that's what I did over here with this little thing. Let's take it apart. All right, taking a look at this, you have your 2 controls. You have your volume, just like in the schematic, and you have the gain control. And again, you can raise this pot to a higher value if you want more gain, but I really don't want this to be high gain. I don't want it to increase the noise level or anything like that. I want to keep it pretty much close to unity. That 3 dB is just enough to kind of restore any dropout or anything and give it a little bit of extra signal if you need it, but typically you shouldn't. Now, input and output, and that just kind of fits right in here like this, and you can see most of this inside here is the power supply. This is a tiny little toroid transformer giving you plus and minus 9 volts, just like the batteries were in this mono version. And right here is the actual circuit on this little board, and you can see it. The 2 channels are just separate. There's one chip, there's the other chip. And you can see it's so simple. You have the little input capacitor and all the little resistors. And then you have the 2 potentiometers wired in. This is just an eBay purchased module for, you have your AC input, and then it rectifies the AC and regulates it to plus and minus 9 volts. And you do need a virtual ground for this. So what do I mean by virtual ground? Well, if you look, the way this thing's designed, it uses a positive 9 volt and negative 9 volt power supply, but there's no ground in here. The ground is actually derived, the center point, from the input and output signals. And they reference to ground only when you apply a signal to it. So it does use a split power supply with they call this a virtual ground setup. And there's ways to do this without having a plus and minus power supply. In other words, you can take a single DC supply, like a single 18 volt supply, and there's a little circuit that you could build that will create that virtual ground. And it'll create a split power supply from a single power supply. But rather than do that, I had these things, so I just built it this way. So let's see how it looks, or how it works. Here's the scenario. You can see on channel 2, I have a 500 hertz 1 volt peak-to-peak signal. Channel 1, I have a 1 kilohertz 1 volt peak-to-peak signal. So we can see the 2 different frequencies. And it's 1 volt peak-to-peak. If we come down to the little box, it just comes out of here, plugs straight in, comes out of the box, and goes into the oscilloscope so we can measure it. And if we look, we're at 200 millivolts per division. So we have 2, 4, 6, 8, 10. So it's just a hair under 1 volt peak to peak. Actually, I think if I move this a little more accurately, there we go, there. Exactly 1 volt peak to peak. So it's unity gain. And if you look, I have the volume turned all the way up, and I have the gain turned all the way down. Right there. Hopefully you can see that now. And if I increase the gain, it should give me just a little bit extra. It won't quite double it. Now it should with mathematically, but it doesn't. It'll be a little bit. And you can see it's pretty close. It's pretty close to 3 dB gain. So not bad. There you go. Nice. And the beauty of this is, once again, it isolates the signal generator from the scope in this instance, but it will also isolate your signal source from the device that you're driving. And better yet, when we're plugging, let's say we were going to plug this into the microphone input of the camera. I can actually turn this down, and let me turn these back up to where they were, and I can actually decrease this quite substantially and bring the signal level down to where it needs to be so that the microphone jack of the camera doesn't get oversaturated. That's the purpose of it. It's a very simple device. That's all it does. Now, of course, you all know me, and there's a little power switch to turn it on and off. I can't leave well enough alone. I got to thinking about this, and I said, well, this is a really useful device, but there's a lot more that we could be doing with this. Namely, if you remember, I showed you one of these things, and this is called an Reverse-RIAA adapter. So this takes a line level signal and reduces it down, putting the opposite of an RIAA curve on it, so that you can use your line level signal to drive a phono input. So if you want to test the phonograph stage of a receiver, you can plug your line level signal, like let's say your computer line level. You can plug that right into here, and you can plug this into your phono inputs, magnetic phono inputs of your receiver, and it'll let you test it. And I thought to myself, boy, wouldn't that be nice if we had the option to do that as well? That pretty much I could use this to drive, you know, connect a vacuum tube device to, you know, to the input of my camera. I can use it for testing a phono stage. I can use it for attenuation if I need to turn the signal down. It has a lot more versatility. So here's what I came up with. Here's our next iteration, and this actually turned out to be the final product, at least for now. I have some other ideas that it may evolve even more. But using components that I had, I designed a little driver power supply, and it's just a simple transformer, bridge rectifier, and 2 voltage regulators, which really you probably don't need these because of the way this works, but I put it in there anyway to filter it. And then that's driving our same signal, but the only difference now, see, this should look familiar to you, but I added this little Reverse-RIAA stage and the ability to bypass it. So this filtration network here, what it's going to do is it is going to put a Reverse-RIAA taper, or curve I should say, onto the audio signal that you're driving into it. It will also attenuate the signal down to the voltage level or to the amplitude level that a phono stage requires. And then if we want to just use it as a line level buffer amp or buffer preamp, then we have this switch that will bypass this whole filter network, and this switch which will disconnect this resistor right here that goes to ground because it clamps it off at 1K or 1,000 ohms. So I will actually use a 4P DP 4-pole double throw switch. So all 4 of these things will be wired up, so with one switch you can flip it and you can bypass this or switch it in or out, however you want it. And then of course you still have the gain, and this becomes important because this filter network will attenuate the signal a little bit. And I don't mean just from the RIAA curve, but I mean it will actually overall attenuate it. So this allows you to kind of regain some of that loss through this little gain pot. So it's a very versatile little circuit. Now, what I'm thinking of doing down the road, I might do, is even add the option to have a balanced output as well, because this is of course this is a regular RCA unbalanced output. But that's a future project. I really don't work with balanced inputs very much in audio, but sometimes, so I might do that. Let's take a look at the final product. I decided that the project was getting a little bit too complicated to just work out on a proto board, so I decided to go ahead and make a printed circuit board. So I mapped out a printed circuit board, and if you notice, I left some open space here in the corner and a little bit of space on this corner, that if I decide to add that balanced output adapter, I can put that circuitry in here as well. And then I printed out the Gerber, plotted the Gerber files, and I sent it off to JLC and just had a prototype board printed up. It's very inexpensive. And here's what it looks like. There's the board. Pretty simple. And I'm using the same type of little toroid transformer. I bought a group of these. There's you can get these on, I think you can get them on eBay. I bought a bunch of them, not a bunch, but a few of them a while back. So it worked out for this. And these are only 9 volt. And really, for a 9 volt supply, using a 9 volt transformer is not ideal. What this should have been is a 12-0-12 or a 10-0-10. But because this is such incredibly low current, you're not going to have any ripple, because the peak voltage is 1.414 times the 9 volts, because this 9 volts is RMS. So we still have above, these caps are charging up above 9 volts, and then these regulators are clipping it off, and you have about a 1 volt drop on these. So you have to have at least 10 volts in here, give or take a little bit, to get 9 volts, a nice clean regulated 9 volts out. So that's what this is. Here's the 2 channels, and of course my proto board, I messed up. I don't know what happened, but when I plotted the tracks, I swapped the plus and minus around. So if you notice, here's a little bodge repair here, and it goes on the bottom, and another bodge repair here. I ended up having to swap the plus and minus to the pins, because I had the plus going to the wrong pin and the minus going to the wrong pin on the chip. But that was a little tiny thing. I made the repair on the Gerber file. If I decide to order more boards or order another board or whatever, that's corrected now. So then we mounted it up in a case. Let's take a look at that. And here it is, all mounted up in a case. You can see on the back, I just put one of these little IEC receptacles with a built-in fuse holder and a built-in power switch to make it neat. And this was just a little metal chassis box that I had. I turned it upside down. I didn't have the cover plate for it, so I just used a little piece of wood. Let me take the cover off. I'll show you the inside. And here it is, all mounted up inside the case. Nothing to it. So here's the... And if you notice, I did not connect earth ground. In other words, this chassis is not connected to earth. All of these are common to the chassis, but these are going to be common to the device under test and the source. So it ties those together, but we didn't want to add another ground in there, so you don't get a ground loop and you don't get earth noise from the earth ground, especially if something's plugged into an isolation transformer. This transformer provides isolation. So this whole power supply is isolated from the outside world by the transformer. And that's why I did it that way. Let's connect it up and listen to it. Here's the setup. We have the audio interface coming out of the computer right here. It comes out of that and goes into the box. And one of the problems I had in the past was that audio interface, when you plugged it into other things, especially like the bench amplifier over here, which is what we're plugged into, we would get, sometimes you'd get some buzz and some crackly, Now I can turn this up as loud as I want, and there is absolutely no noise. It is dead silent, which is exactly what we wanted. I have the volume turned all the way up. So that means everything is set to unity gain right now. And I have the gain set to minimum. So there's no gain in the circuit, maximum volume. So that means whatever's going in here is exactly what's coming out here. And if I turn on a song, a YouTube friendly one, okay, you heard that through the microphone. I'm going to now disconnect the microphone, and I am going to come out of this and go right into the microphone jack of the camera and play that same track. Okay, I didn't listen to it, so I don't know what it's going to sound like, but when we play it back in the video, hopefully it will sound much better than it did before. And if you notice, I had to turn the volume down to here. And this is a logarithmic taper potentiometer I put in here. Both of these are logarithmic. That's because that's what I had. Maybe in this instance, a linear taper pot, at least for the gain, would be better. Maybe the logarithmic would be okay for over here, but it doesn't matter. It's all about, just where you have to adjust the pot. Anyway, that's what this is and what it does. I want to show you one last thing here. All right, we are now connected to a Phono Preamp. What this does is this takes the Phono, if you take your Phono cartridge from your record player and you plug it into this box will add the RIAA curve and boost the signal to a line level so that you can play it in a line level stereo. So this is the same as having the phono stage in a receiver. So this is simulating a phono stage in a receiver. Any of you who have ever plugged a line level signal into a phono input will recognize what it sounds like when you do that. So that's what we've done right now. The switch is down. This is in line level mode, and we're going to feed that line level signal into the phono stage and listen to it on the amplifier. Okay, I have it set up. And I get a lot of emails from people that are just getting new into the audio field, and they say that they got a receiver from their dad or their uncle or their grandpa or somebody, and they connected something up and the phono stage sounds broken because it's very distorted. And it's because they don't understand that a phono input is a completely different level than a line level input. So let's play this, and this is what it's going to sound like. Pretty awful, isn't it? Okay, now let's just flip this switch and let's start it over again. Amazing, isn't it? So that's what this Reverse-RIAA does. So with this little box, we can connect our signal into the microphone jack of our camera. We can connect it to a normal line level input of anything, whether it's a tube gear or transistor gear or whatever. And you can even drive a phono stage on a receiver. And that's the purpose of this. So I hope you enjoyed this little show and tell. This was just a quick video here. Didn't get into a whole lot of details, but thought you'd be interested in this type of thing. And maybe this will inspire you to want to build one yourself. You can go back, and if you want to do a screen capture of the schematics and so forth, you can go ahead and do that. Anyway, I wish you all peace, joy, happiness, and good health in your lives. I hope to be getting some projects back up here on the bench in a little while. Things hopefully will settle down in the next month. It'll probably be within a month, and we'll be able to get some interesting things on the bench that I really am looking forward to working on. So until then, I wish you all well, and we'll talk to you soon, and we'll probably do some more little projects like this along the way. And yeah, take care.